To continue now, we have to Professor Diego Souza introduce to Professor Hannes Schmidt. You can start, Professor Diego, please.
Okay, thank you very much, Juan. So for us, it's a great pleasure to introduce Professor Hannes Mais Schmidt from FAU University in Erlangen. Professor Hannes, he's a assistant professor in Erlangen, and he defended his PhD in 2017 at Germany, and then he moved to Rincon as a postdoc in the group of Professor Karl Kunisch. And since March of 2021, he's assistant professor there in Erlangen. Has several publications, very good articles in very good journals. And today he's going to talk about a renormalized solution for optimal control of the drift in Fokker-Planck equation. It's a joint work in collaboration with Professor Christian Lang and Karl Kunisch. Thank you, Professor.
All right, yeah, obrigado. Thank you for the introduction. So thanks for having me here. It's a great honor to be in this seminar. So I was awestruck when I looked at the list of previous speakers. So this is it's very nice for you to give me this opportunity. So thank me for that. Yeah. So it was already mentioned. So my talk is about renormalized solutions for optimal control of the drift in Fokker-Planck equations. This is a topic which I started to develop together with Karl Kunisch when I was a postdoc with him. I think he was also a previous speaker here in the seminar. And also with recently with Christian Lange. It is nice that you called him professor, but he's actually my PhD student. So, but he's going there maybe eventually. Yeah, so is that. So it was already mentioned. So I am at FAU Erlangen-Nürnberg in the group of the chair of Enrique Zua-Zua, so chain dynamics, control, machine learning, and numerics. All right. So what is the problem that I'm going to look at today? So it's an optimal control problem with a Fokker-Planck equation. So what do we have? So we have an optimal control problem consists we minimize some objective function consisting of two functions to be minimized, which is y and u. Y is the state, which is the solution to this Fokker-Planck type equation here, and u is the control that we imagine that we can manipulate in the system. So this is a Fokker-Planck type equation. So we got a time derivative. We have a second order elliptic operator in space with a symmetric matrix sigma transpose. That's a classical way of writing this. And what makes this a Fokker-Planck equation is that we also have a first order term, which I'm writing here in conservative form, divergence alpha u times the state y, and you can already see from the way I write this with alpha and u, the setup that I want to consider is that this drift field, which we have here, alpha and u, that decomposes in a temporal component u of t and a stationary, so non-time dependent spatial component alpha of x. Right, so I suppose that this drift field here is given by alpha of x times u of t. Okay, it decomposes in time and space. And the thing that I'd imagine or that I assume that I can control is the temporal amplitude, so to say, u of this spatial drift vector alpha. And what I want to do is I want to manipulate this u in such a way that this objective function up here is minimized. And what does the objective function say? Well, what it wants is that I drive the state y to a given trajectory yd over time and space, okay, in a kind of mean squared error type. All right, so and we look at this problem on the whole R of D. So that is motivated from certain applications in stochastic PDE, so to say, where it is kind of well known that if you have a stochastic PDE, like that here, stochastic process, then the associated probability density functions, they basically follow this Fokker-Planck type equation. It's not exactly that one, but it's close enough. And that what motivates us from looking at R to the D, and in principle, D is going to be very large. Okay, so I'm not going to. So what I will not be able to do is leverage any kind of good Sobolev embedding or something from that because D is we assume to be very large. All right, but in principle, we could also consider a bounded and smooth domain with, say, Dirichlet boundary conditions. Okay, that the theory would still be fine. And the whole thing is complemented with an initial value. All right, so that's just looking at the problem. So that's a so-called bilinear optimal control problem. Why is it bilinear? Well, because there's a product u and y between the control and the state. Okay, that's a bilinear optimal control problem. So the equation is still linear in y, right? So it's a linear equation in y, but it's a bilinear optimal control problem. All right, so what is the basic assumption and what motivates this whole problem? So the motivation that we had is there is a bunch of applications where people manipulate microscopic particles with a laser, so-called optical tweezers. You can read this up in the book of Riskin about Fokker-Planck equations. And there, what in particular occurs there is that the potential, so basically that drift field here is the gradient of a so-called potential. They are non-smooth, so there's an interesting work by Oliveira, 2019, which basically says that this is an interesting problem to look at. And there the potential is basically of a W form, which means that the gradient is piecewise constant. All right, so that means that this function alpha and u here, in particular the alpha, is going to be non-smooth, which is an interesting obstacle to look at. And there has been previous work on optimal control of such Fokker-Planck equations. Interesting, most of them are kind of recent. If you look at the years here, so that's Fleigl and Guglielmi, Breiten, Kunisch and Pfeiffer, and Soledad Arona and Freddy Trölsch in 21 here. But what they all do, so what distinguishes our work from this is that we assume much less regularity on all the data than they do. Okay, which is, as I said, motivated by this application, the optical tweezer. Right. So what are the assumptions? The assumptions are as follows. So I just listed them here. You don't have to remember all of them. Okay. When I'm going through the talk, I will remind you of what was assumed. So as I said, so we assume that the drift field here, alpha times u, I'm usually calling this B, that decomposes into temporal component u, spatial component alpha. The u I assume to be non-negative because I will have here is a sign condition on the alpha, so I need to impose a sign on u as well for that to make sense. So u is going to be non-negative in L2, and alpha is just a bit more integrable than 2. Okay, so usually L2 would be enough, but later for the analysis we actually need a little bit more than 2, so this is slightly more than 2. So in particular, no Sobolev regularity, no BV or anything, just a plain vector field in L2, a little bit more than L2. We do have an assumption on the divergence of alpha. Okay, so alpha is not a Sobolev function, but the divergence of alpha, so to say the trace of the Jacobian, that we assume to be a regular distribution, which is a bit more than 1 integrable, and the negative part is actually bounded. Okay, so that's technical assumptions, but this is basically the lowest that we can go, that what we can do. We have the diffusion matrix here, sigma, that is not supposed to be bounded, it's just to be an L2 function in time and W12 log, so Sobolev regularity in space, locally. And for this talk, for simplicity, we assume that it's uniformly positive definite. Okay, so this is really a parabolic equation. So we can do a lot of what I show you next. We can also do if we do not assume that the problem is strictly parabolic, really parabolic. So we can do still quite a lot if we dispose of that. But at some point later, we're gonna need it. But we haven't figured out how to get around it on 1 or 2 places. So I'm just leaving this here for this for the sake of presentation. That is, by the way, what allows us to not have any kind of BV or Sobolev regularity on the alpha. The initial value is supposed to be in L1 intersected L infinity, so in every LP space on R to the D. And there are, for the involved functions like sigma and alpha, there are a bunch of growth bounds for x going to infinity. So basically sublinear growth at infinity, but this is kind of technical and you won't see it in detail, so I'm just leaving it out. Okay, but this is, since we look at the problem on the whole space, there's going to be some growth bound far out to make sure everything is fine. And all of these motivations, all of these assumptions, we didn't invent most of those. They come from, if you look at classical papers about the analysis of transport and Fokker-Planck type equations like those. So if sigma is 0, then this degenerates to a transport equation, right? This is Di Perna and Lyons, Ambrosio, Le Prix and Lyons, Luo, and again Le Prix and Lyons. So Pierre-Louis Lyons, I think he actually also was a speaker here, so that is very fascinating to me. And they have worked extensively on the analysis of these type of equations, and that is basically what has been managed so far in assumptions, and we are going to take that as a blueprint for the optimal control problem. All right, and if we pose these assumptions, then we can actually show that the state equation, so the standard Fokker-Planck equation here, that this is a well-posed equation, which says that for every control U non-negative, there exists a unique weak solution to this equation, with the regularity that y is in L infinity with values in L1 intersected L infinity. That was what we assumed for the initial value, so that's kind of the trace space, and we have that the gradient is in L2, L2. Right, so but there's no time derivative, okay? So when I say weak, I mean that we integrate to weak formulation in time as well. And what is particularly interesting here is that the y, so the solution, is a so-called renormalized solution, which means that it satisfies this additional PDE here in the sense of distributions on time and space. And what is this PDE? Well, the PDE is a PDE for beta of y instead of y itself. Okay, it's a PDE for the nonlinear modularization of y in terms of beta of y. Beta is a C2 function. And you see here, so the first three terms, they are exactly the ones that we have up here, just for beta of y. And then there's the error that we make, which is these two terms. Okay, and the way you get this formulation here is formally you multiply this equation formally by beta prime of y and then reverse the chain rule. All right, and that's totally consistent with the original equation, because if you take beta is the identity, then everything, this guy collapses because the identity is second derivative is 0. And if we have the identity, then this also collapses, right? And for the identity, just this part remains, and this is the original equation. All right, and that's a very interesting property. All right, and let's briefly go through how we do that, because we need a bunch of details from that for later on. And for good measure, so in the original equation, I did not have a g on the right-hand side, so I just had a 0, so I just put a g here and assume that the g is in L1 and intersected, and L1 intersected L infinity in space, which is a bounded function in every LP space. I call the function solution P now, and I consider general vector field B here, so general drift field, which just has the assumption that the negative minus the negative part is bounded above by an L1 function. Yeah, that's a general assumption that we actually need. This is encoded in the assumptions that we had before. All right, and what do you do to get some solution is you modify all of the data in the PDE and look at the associated, well, smoothened epsilon PDE, so to say. There's a bunch of smooth solutions to that, because if we modify all this data, well, all the data is smooth. It's a problem on R2DD. We get a nice and smooth full solutions. You can look this up in the book or paper of Igari, for example, even if the sigma here is non-positive definite. Then we get, this is a very nice PDE then we get a bunch of a priori bounds on the solution of the modified PDEs. From these a priori bounds, we extract weak star subsequences in the corresponding function spaces, because we get a uniform bound. We pass through the limit. That gives us a weak solution to the original problem. This is very nice because we keep the bounds for the limit solution. However, this gives us some solution, not a unique solution. Okay, so just a more or less constructive way of getting a solution. Okay, so again, we smoothen everything in the PDE, look at the smooth PDE. This has a smooth solution. We derive a priori bounds. We extract subsequences. We get a solution which satisfies still the bounds, but is maybe non-unique. Okay, so how does this work in a bit more detail? Is so a simple bound on so this is here you have the smoothened PDE where I put an epsilon to everything. From the maximum principle for this PDE, you get an L infinity bound in terms of the L infinity norm of the initial value and the L infinity norm on the right-hand side. And since modifying is at least sublinear with respect to the L infinity norm, we get the original data bound here. This is the C here. It's the one which is the upper bound for the negative divergence. So here you see how the assumption on the negative divergence of B enters the estimate. This is a maximum principle. This is kind of abstract, but you can, of course, this is a very nice and smooth PDE, which holds pointwise in every time and space point. So you can just go ahead and test this with the absolute value or regularized absolute value of the solution, and you get an L1 bound in space, which has basically the same right-hand side where we have L1 instead of L infinity. And then at least what's my first instinct, I don't know how it is about you, but I've learned a bit about function spaces, which is that I interpolate between these two estimates, of course. And I get an LR bound in space, so for R between 1 and infinity for every R. So that works very nicely. And again, testing the PDE with P epsilon itself gives us also a bound on the gradient in L2 in terms of all the data, but the bound isn't as nice as before, so I'm just writing here, absorb all of this in a constant. Right, but it's a finite number given in all of the data. All right, so I have a estimate in L infinity LR and an estimate in L2, which is all uniform without epsilon, so I can extract a subsequence of in these two norms, so to say, and I get the limit P and gradient P, which then allows me to pass through the limit and get a weak solution from passing to the limit here. All right. Now, or sorry if you can hear it, but it seems our baby doesn't want to sleep today. So let's see. All right. So that gives us some solution. I just showed you how. Now, uniqueness. How would uniqueness follow? So I told you before that the solutions that we consider, they have this particular property of being renormalized solutions. And in fact, this is not just a nice property to have, but it's actually the key to getting uniqueness in this setting. And the key to getting uniqueness, it works as follows, is, so I wrote down for you, this is what it means for the solution P to be renormalized. Okay, again, beta of P satisfies the PDE, and then we have the correction terms here. And this works for every sufficiently smooth function beta. So in particular, for the very simple function beta of S is S squared. So what happens if I insert beta of P as P squared? Well, I get here P squared, P squared, P squared. This here reduces to plus P squared, and this here just becomes 1. So it gives me this equation. Okay. And now I immediately see, of course, this guy is non-negative, so I can leave it out and get an inequality. All right, so this is where I start on the next slide. So I suppose I have this renormalization property. So I just want to show to you how this gives you uniqueness. Okay, and this is by picking the square, getting this equation still in the distributional sense. And as I said, so imagine your head will replace this and make this an inequality. So what do we get then? Then I go ahead and multiply the whole equation. So formally, I test with a flat bump function for the ball. So that's basically, I get the flat bump function for the R ball by taking the bump function for the one ball, so for the unit ball, and scale that guy. I test the whole equation with that. I plug everything to the other side. I get an inequality for the time derivative of P squared times phi R with a bunch of terms here. And what's interesting is that from the construction of this flat bump function here is that when I have a gradient here, I have kind of 1, because if I then drive the R to infinity, that will make my bump function very flat, which makes all these gradients basically disappear. And I'm left with these two terms. By driving R to infinity, that kind of gives me a bump function for the whole space. So this just gives me an integral over the whole space. This is bounded by minus P squared divergence B, and we remember that we had an assumption on minus the negative part of divergence of B, namely that it was bounded by this L1 function C. So what I get is an inequality of the integral over P squared in terms of itself, so to say, time derivative against itself in the distributional sense, and luckily there's a distributional Grunwald lemma, which then tells me that the P must be 0. So that is kind of nice because, of course, I did the whole thing when I talk about uniqueness. I want to talk about the case where I have initial value 0. So now I have a function which initial value 0, and I do know that it's constantly 0 over the whole time interval. So that means my solution is actually unique. Okay, so solutions are unique in the renormalized class. So now it basically only remains to show that every solution that I derived by this approximating procedure in the first part of the discussion, that this is actually renormalized. All right, and how does that go? So again, we saw uniqueness follows from the renormalization property. So how do I get the renormalization property for the given solution that I had, or for any weak solution? Well, I told you right in the beginning, what I formally would like to do is I would like to multiply this equation by beta prime of p and then reverse the chain rule, right? So to get the beta of p in the derivatives. But I can't, because if I have a weak solution, well, then the weak solution I can't just multiply by some function which I have no a priori info about the regularity about. So what you do instead is you modify the whole equation. You do know, okay, in a distributional or in a weak sense in the appropriate function spaces, this differential operator applied to p here is 0, so it stays 0 if I modify this with a suitable modifier. And then doing all the modifications with these terms, I get a bunch of very complicated or more or less complicated expressions. But what I can do is I can express all of those in the differential operator applied, so the Fokker-Planck differential operator applied to the modified solution up to some error, right? And the error is R epsilon. This now is a smooth thing. Okay, so at least, well, more than that. It's actually not smooth because there's still B and sigma in there. But it turns out this is an L1. So this is true. This is an L1 function here. So the equation holds really pointwise. So I can actually multiply, as I wanted to do before, by beta prime of p epsilon and reverse the chain rule, as I wanted to do all the time. Multiplying p by multiplying like that, reversing the chain rule, gives me this lengthy chain that we had before. This is exactly what we got from in the renormalized solution concept. And the error term beta prime of p epsilon times R epsilon. Okay, so now what we'd like to show is now that if I drive the epsilon to 0, okay, so for epsilon to 0, I would like that this guy goes away. This is what we would like to have. And luckily, there's a very famous result on that, the so-called commutator lemma, or the commutator estimate. All right, so what I want to have, again, I would like to have this error term multiplied by beta prime of p epsilon to go to 0 in the distributional sense. How do these terms R epsilon, these error terms, how do they look like? Well, they are basically exactly the difference. So recall, let me go back one slide. So recall what I did here. I modified the equation, the whole equation, by a modifier p epsilon. And then I claimed this gives me, say, the equation applied to the modified solution, so to say. And now the error that I make is exactly the error, for example, for the first order term here, is exactly, or for a first order term, is exactly the error that I make between modifying this expression and applying B to the modified solution. That is exactly the error that I make. And that is, if you look at that structure, that's a so-called commutator between rho epsilon, the modifier, and the differential operator applied to P. And as I said, so there's a very famous, these are very famous. It's popularized, I think, mainly by Di Perna and Dions 89 with an extension by Ambrosio 2004 for the BV case, which is very nice, which basically says that if the integrabilities of these things which are modified here, so G and F or H times gradient and F, if these match in the correct way with the alpha 0, R0, R1, alpha 0, alpha 1, to certain betas, then this whole modifier, this whole commutator, it converges to 0 in the correct Lebesgue space. And now basically I don't want to go through all the terms, but this is basically it's exactly, of course, the assumptions that we pose are made exactly such that exactly these guys, all these guys in the residual here, that they converge. So that's a bit of tedious work, right? So I'm leaving out a lot of details here because this is kind of very exhaustive to check. And this is actually also where we need the Sobolev regularity for the sigma terms, right? So if the sigma terms here don't have Sobolev regularity, then this commutator estimate won't work. And anyway, if we do that properly, then we actually get the renormalization property for every solution P in the regularity class that I mentioned before for the solution, back then it was called Y. And that gives us uniqueness. All right, so that's a very, very rough blueprint of the several steps that we have to do. Right, so again, we construct a solution with a priori bounds. We show that the solution is renormalized, and how do we do that? By, well, modifying the equation and driving the error by epsilon to 0, and thereby using the commutator estimate. All right, and if we do that properly, we get a solution that it gives us the solution y, so we can get back to our optimal control problem, which was that. So now we know that a solution to the main equation exists and how it works. So what we have is basically a well-defined so-called control-to-state operator. So for every control u, I get a unique solution y to this problem in the weak sense, which means I can parameterize this whole optimal control problem just by the control u instead of looking at the u and y as distinct variables. So I parameterize everything by u, and it gives me the so-called reduced optimal control problem, which is just an optimal control problem in u, where instead of y in the objective, I now have the solution y for the control u to this equation. Okay, so the equation is basically hidden in here. All right, so I have now an optimal control problem just in one variable with a very simple constraint, but I've made the objective function much harder because there is now the control-to-state operator in here. Now, what I eventually would like to talk about today is optimality conditions for this optimal control problem. So conditions which characterize the optimality, the fact that a solution is optimal to this problem. And for that, you maybe I think you learned that in school already, that you would like to talk about first-order derivatives. So eventually, we would like to differentiate this this function yu here, so u mapping to yu, control-to-state operator. So let me say, so in principle, if I have that form and I have a well-defined control-to-state operator, things seem kind of fine. There are a lot of good books and very comprehensive results on how to put such optimal control problems in an abstract framework and then get optimality conditions from abstract conditions. However, it will, in our case, turn out, and this is the main reason I'm researching this topic, that this won't work that easily. And why it won't work, I'm going to show you next. So the thing you would investigate when trying to do the standard theory goes by the implicit function theorem, which is basically, sorry for me going back, is that you basically write u mapping to yu, this control-to-state operator pair. You use that to define an implicit function solving this PDE, and then you show that a certain derivative of certain derivatives of this PDE operator are invertible, and then the continuous differentiability of that control-to-state operator follows automatically from the implicit function theorem. It's a very nice application of that theorem. And the equation you would look like is the so-called sensitivity equation, which looks like that. It's again the Fokker-Planck equation. It's basically the linearization of the PDE, which is, in our case, it's a linear PDE, so that doesn't change anything. It's still the same one. But on the right-hand side, there is the derivative of the PDE with respect to the control in direction h. So the derivative of the PDE with respect to the control is just in that term here. So we get minus that guy on the other side, and we have inserted the direction h in which we want to take a derivative. And the initial value becomes 0 because there's no control in there. All right, so now what you would need to do is discuss this equation. Now, if you look at that equation, that looks kind of unpleasant because that is a distributional first order term, right? So that's a first order distribution here. So that is kind of bad because it doesn't fit in the framework that we had before. That is actually extra bad because it's a distribution. However, under our assumptions, in particular, since we assumed the problem to be parabolic, which makes it much more easier here in this case, is that you can observe that this expression here, so alpha times gradient y plus divergence alpha times y, that this is actually an integrable function. And with that, you can show that this right-hand side guy here is actually a regular distribution, and it satisfies the product rule, giving you this term. Okay, of course, it works kind of backwards, since that basically by knowing that this is integrable, you can show the product rule. This is kind of what the trick is about. So what we then have is, so since we know that now the right-hand side is a regular distribution, we do know the right-hand side here, this is a regular distribution, so it's an integrable function, can be represented by an integrable function. But still, this does not fit at all what we had before, because before we had assumed that the right-hand side is L infinity. And this was also crucial in deriving a maximum principal bound. right? So we have used the maximum principle in the derivation of solutions before, so that doesn't work anymore. So we now have to kind of discuss again what kind of concept of solution we want to talk about for this particular equation. So I've summed this up here again. So imagine we try to reproduce the same formula that we had before, the same principle for the original PDE with the right-hand side G, which was L infinity. Now, in this case, we just have that the right-hand side is L1 and LR, and the R is really just a bit more than 1. This is where I use the integrability, which is just a bit more than 2 and just a bit more than 1 from the assumptions at the beginning, right? This goes in here. We could still modify the whole thing and get for the solution to the modified the equation with the modified data, get an a priori bound like that. This would still work fine. So the solution satisfies an a priori bound in L infinity LR. But if we look back in the equation from our assumptions on the alpha, integrability R, which is very close to 1 in space, won't be enough for that, like for that inside here to be integral. So that's not even a well-defined distribution. Okay, so with the a priori bounds that we can derive, and we won't have much more at our disposal, we won't get a limit in this first order term at all. All right, so we can't do the same steps as before. And even, let me just mention, even if we could, the commutator estimates that we have used, they are very sharp in using the L infinity regularity of the original solution, which we do not have here. So even if we could pass through the limit in that term, we could not do anything in the commutator estimates. So it fails at double places, so to say. Okay, so what do we do? So we need to understand what this equation is doing. So what I am proposing is that we replace the Z in that equation actually by beta of Z, because kind of the culprit of the whole thing is that the Z, the solution to that, is not going to be bounded. So I'm putting myself in a situation where the solution is bounded by looking at the beta of Z in a renormalized way. So how does that go? It goes as follows. So what do? Is we approximate the right-hand side by bounded data, which is exactly of the class that we had discussed before. Then we do know that the associated equation with the right-hand side GK here, L infinity right-hand sides, they have unique solutions which are renormalized. And what I do is I pass to the limit in the renormalized form of solutions. That I can do because now this here is well-defined. Going over to the limit here is well-defined. So I can do that. And by doing a bunch of analysis, so it's kind of non-trivial, but you can do that. You can show that actually the solutions converge weak star in L infinity LR, and the gradient terms do as well. So the guys in here. So that's a bunch of work. So there's a book by Lebris and Lyon where this is done. So you can show that these converge, and you can use that to converge in the renormalized form, which gives you that this problem, so again, we look at the general problem with the G on the right-hand side, but now the G is unbounded, it's in LR. The initial value is also in LR. We can just do that on the side. We don't need it for the discussion of the optimal control problem, but we can do that on the side. And there exists a unique solution, which is in the regularity class L infinity LR, and a rescaled gradient here is in L2. So if R is equal to 2, then this collapses to gradient P at last. In the so-called weakly renormalized sense, which is that the solution is true only in this renormalized sense, in the distributional sense with all the error terms for beta, for every bounded function beta in C2, which has a compactly supported derivative. Okay, so we have to restrict the admissible test functions here. Okay, and that's very interesting because now what we have here is that the so-called sensitivity equation, which is very central to discuss optimality conditions for the optimal control problem, does not have a linear, standard, weak, or something solution concept, but only this nonlinear renormalized solution concept. That is what makes this problem very interesting. So let's see what we can do. Yeah, so sorry, I forgot to mention one thing, and that the nice thing is that we can keep the a priori bounds that we had for the approximating solutions in L infinity LR. That's going to be important. Okay. So what I would like to do is I would like to derive a gradient for this optimal control problem. This is where I usually use the implicit function theorem for. And this is what is not working anymore because I have now just a very weird notion of solution through the linearized sensitivity equation. And now I try to attempt, what I do is I attempt to prove Frechet differentiability of this objective function, which I call J, by hand. So I look at the difference J of U bar plus H minus J of U bar in a designated optimal point U bar. And I do some clever manipulations of this squared objective function here. I get the difference between the two solutions, y of u bar plus h minus u bar, some kind of direction, y of u bar plus h minus y u bar, in direction of what is up in here, and the residual terms for the second order, for the control cost term. These are kind of straightforward. And the idea would be to show that this first term here is of order O of small h, so it's actually kind of Hölder continuous of order a bit more than 1/2, and that the second converges to the gradient as h goes to 0. This is what I would like to. So the gradient of this first part, the second part is easy. This is what I would like to do. Okay, and how do we do that? So the first term, so that's the difference y of u bar plus h minus y u bar. That is actually, if I subtract the equations satisfied by these two solutions, I get that equation up here. It's again the Fokker-Planck operator applied to the difference, and the right-hand side looks familiar to the one that we had before, just that there's the shifted solution in there. But I do already know that both of them are weak solutions in the L-infinity regularity class, so I don't know that the ZH, which is their difference, is uniformly bounded in L-infinity, right? Because both of them are. Now, the right-hand side here is, again, by the same argument as before, it's a regular distribution in L1, LR, with the R slightly larger than 1. So I get the a priori bound from before, which is LR here, and it gives me an a priori bound against H, which is basically the non-constant thing in here, because it's parameterized by H, on the right-hand side. Okay, everything else is uniformly bounded in L2. Now, of course, I interpolate again, and I get an L-infinity bound in LF in space. So I interpolate between R and infinity, and it gives me an LF in space with that right-hand side with the power R over S. Right, so if I take S to be R, I get the power 1, which is that guy. If I take S to be infinity, I get 1, which is that guy. Okay, I get this nice estimate here. And that is actually, I'm nearly done. So here's again the attempt at Frechet differentiability. So that is the guy I want to estimate, which goes to 0 in small o of h. Now, what I had before is, so this expression here is just the L-infinity L2 norm of ZH. So actually here's just the L2 norm, but here's the L-infinity norm. So I get this in L2. And now I write L2 as a convex combination of 1, so 1 over 2, I write it as a convex combination of 1 over R and 1 over infinity. Using the result from the previous slide, I get that this is of order h to the power R. And now, since the R was larger than 1 by our assumption, this is small o of h. Okay, this is, as I said, kind of Hölder continuity type result for the control to state operator, actually. So actually that works from the way we have constructed solutions for the linearized equation for this sensitivity type equation. So that is nice. And now I claim that the second guy here should kind of converge to the gradient if h goes to 0. Right, this should give me the gradient. And from experience, I know that this will probably have something to do with the so-called adjoint equation, which is derived from the adjoint differential operator of the linearized differential operator, which is in our case the same. Okay, so how does that work? So from experience, I look at the so-called adjoint equation, which is L star Q is YU minus YD. So that is the defect in the objective functional that I'm interested in. L star is supposed to denote the adjoint differential operator to the Fokker-Planck differential operator. And then the resulting equation, which I write formally like that, should be exactly that one. So that is the adjoint Fokker-Planck differential operator, which is now backwards equation in time. So backwards minus here, and we start at P. The second order term hasn't changed, of course, because this was symmetric. And the first order term has changed from conservative form to non-conservative form. So why do I look at this particular adjoint equation? Well, because formally this is the expression I have in my attempt at Fréchet differentiability, where I just replace the yu bar minus h minus yu bar by zh. So if I write it like that, that is kind of like zh in some kind of inner product with L star q, if L star q is just yu bar minus yd. I shift the L to the other side. I get LZH, that is the Fokker-Planck operator to apply to ZH, tested with Q, and that is kind of minus divergence. So LZH, we know what it gives. It gives us the right-hand side that we had before, minus divergence of this expression with Q. So this is why I look at this particular adjoint equation, and you can actually show in a rigorous way that this so-called duality formula is true, that this integration of this difference here of solutions, the solutions, so this guy, so to say, solution to that guy, gives us exactly that expression here tested with Q. So in this case, this is a weak formulation, so divergence goes over to the other side. I get a gradient here, and the inside is here. Okay, that's a so-called duality formula where basically this is made rigorous. All right. How do we do that? How do we make that rigorous? Just a brief roadmap. So what you usually would do if everything was very smooth, you test the adjoint equation with the ZH, you test the equation for ZH with the Q, and then you do integration by parts. And then you basically cancel all the differential operators with each other, and it just remains that one guy here. In our case, the adjoint equation is there only in renormalized form, which is not very nice. So there's a distributional and nonlinear notion. And the solutions, the designated solutions Q and ZH, are kind of irregular. So in particular, they have no time derivative right? So if I test one equation with the other, the time derivative must go somewhere. But if both don't have a time derivative, I'm kind of screwed. So what you do is, again, so this follows kind of a roadmap from a Similia result, which is already there in the 98 paper by Dupin and Lyons, is you again modify both equations, you switch to the modified solutions, you do the whole thing for the modified solutions, so for the smooth solutions to the modified equation. You pass to the limit in the modification, you get a formula in the renormalized sense, and then you approximate the renormalization function by beta. And then you use the growth bounds similar to the Gronwall argument as before. You can probably guess from that list, this is a kind of formidable thing. I think it's like 4 or 5 pages of doing more or less painful estimates of a lot of integrals. But in the end, it works. Okay, so the idea is more or less straightforward, but it actually works. Okay, so that was quick, but let's just briefly recap because I'm nearing my time limit, I guess. So Fréchet differentiability. This was exactly what we had before. So the difference of the objective functions of a solution u bar plus h minus y of u bar expanded in the square plus the directional term plus the parts for the control. So what we had shown is that this guy here in the front, even with L infinity, that is bounded by h to the power arm divided by s, and we had shown that this leads to small o of h for that term. Obviously, that term is also small o of h, so we can absorb them both into small o of h. We get that. Now for the gradient term, what we had here is I am going to insert that what I think should be there plus. So what would actually be there from our duality formula here would be the corresponding expression here with the u bar plus h, but I'm putting the correct one here and putting the error in the next term. Why do I do that? Well, because we already conveniently have down here that exactly the error that we have here, that this gives us a power of h error, which is again of order small o of h, if we do the estimates correctly. So that guy goes away, we can absorb it in here again, and we are left with just these two guys, which is like that. And if we look at that, we have proven that the objective function j is actually Fréchet differentiable with that derivative, because that's a linear derivative in h and a small o of h error. And then having that tells us that the so-called reduced gradient of this objective functional, so the gradient of j, is exactly given by that. So that's a gradient in L2 now, because if you recall from here, right? So we have an inner product against H in the L2 inner product here. Reduced gradient looks like that, and again, the solution Q, which is in here, is the solution to this adjoint equation with the right-hand side, the defect in the objective function. And that is exactly what you would expect to come out from if everything worked as you would hope it does with the standard theory, but you can't apply actually the standard theory, but you have to work quite a lot for this to go on. All right. And having that, you can write down the first order optimality condition, which is the so-called variational inequality. So the direction derivatives in all feasible directions of the constraint set, which is this u larger than 0 here, is non-negative. So basically, you're looking upwards whenever you look into the feasible set. And from a bit of standard theory, you can rewrite that in this nice projection formula here. So the optimal control is actually given by the maximum of minus mu divided by beta, and mu is the so-called adjoint state in here. So this is very nice, and then you can do a lot of optimization theory from there if you like. All right, good. So what have we seen today? So we've seen a Fokker-Planck equation optimal control problem, bilinear optimal control problem on the full space with very irregular data, which forces us to do things very complicated way. We use renormalized solutions for that. We had that for both bounded and unbounded data in the weak and strong renormalized sense. The critical assumption gave us that this right-hand side in the sensitivity equations, this divergence here, is a regular distribution for which we kind of needed, so I don't know another way around it yet, that the problem is strictly parabolic. This gave us a nonlinear renormalized formulation for the sensitivity equation, which forced us not to use the implicit function theorem framework, which is very nice, but we had to kind of do the Fréchet differentiability proof by hand. And what I didn't show you today is, of course, we have done quite a bit more, is that there's weak continuity properties of the control to state operator in particular, which you use to show the existence of optimal controls, right? So I haven't talked about the fact that this optimization problem actually has a solution today. We can also do final value tracking. So our objective function today was basically matching a trajectory in time and space, but we can also do final value tracking. And of course, I obviously omitted a lot of details because they are very cumbersome and complicated and not very suitable for this for a talk like that. And for the future, what we're working on is second order approximation. So can we say something about a second derivative of the object control to state operator? So my personal opinion is that we probably won't get around using Sobolev regularity for the alpha, but let's see. What we'd really like to get rid of is the assumption that the matrix sigma transpose is really uniformly positive definite. So we have a bunch of ideas. Is the classical vanishing viscosity. So add a little bit of diffusivity, derive everything as we just did now, and then maybe pass to the limit in the optimality system. And that would be in particular interesting because the extreme case is the transport equation, which is, of course, a very interesting object. And in transport equation has very interesting applications, for example, in optimal mixing, where the vector field is very irregular, so the vector field alpha in this case. And from the best of my knowledge, the sensitivity equation, which was the kind of the main subject we were talking about here, is kind of also not understood very well in that context. And in the future is, there's also some preliminary work already by Christian, my PhD student, is that we move to actually nonlinear equations in renormalized form, which are then very interesting because then the original equation is renormalized. Not just the sensitivity equation, but the whole concept of solution to the nonlinear equation is renormalized. All right, this is what we would like to do in the future, and then I just scroll over to my references for them to be in the video, and that would be it. And I thank you for your attention, and maybe there are some questions.
Okay, Hans. Thank you very much for your very nice talk. So now we open the turn for questions, comments. So if anyone has a question or comment, please just open your microphone and ask directly to Professor Hans. Well, I will begin. It's very interesting your talk. So thank you very much for giving us the opportunity to hear this interesting topic. My first question is related to because you have only the constraint that the control is positive.
Yeah.
Not if you have an up and bound for the control.
Does not make a difference actually. So the only point where this would make a difference is here.
Yes. Okay.
But like it would still, if it's box constraints like 0 less than u less than some
Yeah.
upper bound, this would just change here the optimality condition and the projection formula. But nothing in the analysis. You just need a so the positivity assumption that we had here is because we assume something on the negative part on the alpha.
No. Okay.
I could, in principle, also omit that and assume something on the whole alpha. That would also work. But since I can do it very sharply in that case, I decided to do it like that.
Good. And the second question is related to that because when we have an below bound and an upper bound, so your control is L infinity. So what about if in your functional you still minimizing the L2 norm of the control, you have an L infinity norm of the control?
Oh, that is horrible. That is horrible. No, I wouldn't do that. No, that's not a good idea. I would rather so first of all, let me say so the control here does not have to be L infinity. It's not automatically L infinity. You could possibly, let me see. You could no, you don't get L infinity actually. So it's not L infinity. Uh, so the assumption that the u larger or equal to 0 I posed, the assumption on the abstract vector field B was that the divergence was bounded by an L1 function. So and that is achieved by u in L2 and the positivity condition. But there is no boundedness. The boundedness was just in space for the divergence. So first of all, and then so that kind of removes the need to put L infinity here, but L infinity here is horrible because that is massively non-differentiable.
Yeah,
like very bad.
You may take an LEP norm.
Yeah, sure. I could. You could in principle also take L1. So in a lot of places, L1 is actually enough. L1 is also known to, if I have an L1 term here, that is also non-smooth, but it's nice non-smooth. You can still do a lot, and it would give you sparsity in time of the control. But I think there's one spot in the analysis where you can't, where you really need the L2. I can scroll back if you like, where I think this is needed. But I think okay, you could of course probably circumvent that with suitable assumptions at some place, but in general, so L2 is needed at one place in the analysis, and of course L2 here is very nice because it gives you this nice projection formula.
And also because when you look at the optimality condition, you have a linear link between the control.
Exactly, that is exactly what's here. Yeah, that is the thing.
Yeah, I know. Okay, and also I have another question is okay, you have your Fokker-Planck equation, so you have the vector field alpha,
yeah,
and let's say the control.
Let me go back for a second. Whoop.
Yes.
Yeah, wait a second. There. Nope.
No.
Still not. Other way around. There.
Yes, exactly. Good. So you have alpha, which is a vector, and you have u, and u is acting in all the components. Okay. So okay, if you have enough regularity, so in some sense,
you mean if u was just acting on part of the alpha? So like you had instead of alpha times u, you had some alpha I ui?
Yes, no, but just because you have, in some sense, is that you have any u's, okay, and all these u's are equal. Okay?
Yeah,
That
yeah.
I would say that you have just
You mean like that?
yes, and there is no control. There is no
Yeah,
and
yeah, yeah.
yeah, exactly. Is it possible?
Yeah, no problem.
No problem. Okay.
No. You could actually distribute. You could have different U's for every alpha. Wouldn't make a difference.
Okay. Okay. And also, my last question is about numerical simulation. Have you?
No, no, not yet. We have this is a question I get a lot. So we obviously have that on our menu, so to say. But because really the linearized equation formally is so I have no idea how to solve the linearized equation in this renormalized sense numerically. Um, Yet maybe
Okay.
the idea comes, but we don't know yet.
So, okay, I lied, but my last question is now
Yeah.
about the infinite time horizon
Yeah.
case. Is it also
Oh, that is a good question. I would think you could still do a lot. Yeah, I think you could still do a lot. Yeah. The analysis would probably not be influenced too much. You need to be a bit careful because I think at some place we surely use that the L2 control is also an L1 control, something like that. But probably something you could get around. From the analysis, I would not see a problem here. But then, of course, well, okay, and time tracking makes no sense, of course. That is out of the question. No, I think you could probably do that.
okay? Okay.
Yeah, but this is something I should talk about with Kai Kunisch, I guess. So this is yes.
Yeah. I think that he did something else with.
Yes, yeah, right. So he has further work on Fokker Planck, but nothing with the present
Yeah.
particularities.
Okay. Very good. So, is there any other question or comment? If not, let us thanks again, Hans, for your very nice talk. So, thank you very much. So,
Thank you.
Oh, thank you, Diego. Thank you a lot, Professor Hannes, for your brilliant talks.